This video is about an integration technique called trigonometric substitution. And you use it whenever you see something that looks like Pythagorean theorem. Remember, that's a squared plus b squared is equal to c squared looking stuff. So of course we all know Pythagorean theorem, but of course I can manipulate Pythagorean theorem. What if I wanted to solve for b? Right, b squared is equal to c squared minus a squared. Well, we're seeing this sort of thing over here. Like here's a t squared minus 16. So in a sense, if you looked at this one, my c would be t, and my a would equal 4. I'm trying to map what I see to one of the Pythagorean theorem forms. So trigonometric substitution is used when you see something that looks like some form of Pythagorean theorem. Maybe we have something squared plus something else squared like we see here. Or we may see something that looks more like this. We have the difference, the subtraction of squares. We may see some number squared, then minus another number squared, like we're seeing that here. So whenever you see something like this, you know to try and use trigonometric substitution. And here's how it goes. So you'll use this table. This is the essence of Trig Sub right here, just memorizing this table. So for instance, look at our first one here. I see some number squared, that's our 1, minus something with x in it squared. That's going to be this form right here. This table looks a little scary because we have this function of x squared thing. But this just means whatever part has x in it squared. So I'm going to use this entry to take on this problem. And I'm not going to use this one because I have a plus sign here. Well, this is a minus sign, so we're not going to use that second entry. And we're not going to use this third entry because what it says is we have something with x in it squared and then the minus sign and then the number squared. Well, here we clearly see some number first, then the minus, and then the thing with x in it squared. So we're going to use the first entry. So we just have to match everything in our entry to what I see in my problem. So my a squared, remember a is just a number. It doesn't have the variable in it. It doesn't have an x, it doesn't have a t, it's just a number. So the a squared is going to be this right here. So I'm going to say a squared is the 1. Then of course we have the minus sign. And now my function of x squared is going to be equal to this big 4x squared right here. So I need to figure out what a and my function f are because this is how we determine which substitution to use. We could use one with sine, one with tangent, or one with secant. Well, if I do the radical of both sides, a is just going to equal 1. And just use the positive option, just positive 1. And if I do the radical of both sides for this equation, I get my function f will just equal 2x. And therefore, the substitution we should use is 2x, that's my f first, is equal to a, which is just 1 times the sine of theta. So this is always the first step of trigonometric substitution, using this table right here, based on what sort of Pythagorean theorem sum or difference of squares that we see. So that's how you would use this table right here. So notice here, I would use this entry of the table because I see some equation with x in it being squared. That's our x squared actually. And then we have the minus, and then we have some number a that's being squared. So a would equal 3 in this case. So just make sure you are comfortable with using this table here on the equation that you see. That's the first step of trigonometric substitution. Alright, so now that we understand how to use the trig substitution table, let's work out this entire problem to see the full process now. Alright, so we're faced with this integral problem. We're going to do it without the bounds, by the way. This is going to be an indefinite integral. So we see our problem, and it looks like we have something that looks like Pythagorean theorem. It looks like we have some number squared plus or minus some other number squared. So we think to use Trig Sub. So our first step is to see what table entry we're going to use. And we're going to use this one because we have just some number squared and then the minus, and then we have the thing with x in it getting squared. So we just have to figure out what a and that function f are. So my a is going to equal 3, and my function f is going to equal 5x. So implementing the substitution choice the table tells me to make, that's going to be my f of x, 5x, is equal to a, 3 times the sine of theta. And of course I can get x by itself. So this is kind of like u substitution, except that I don't have to stress a lot about how to make my u choice. I just follow the table to make my choice. Now, one thing you always want to remember to do is draw the right triangle that the situation describes. Remember, sine, cosine, and tangent, and secant and cosecant and cotangent, they all describe a right triangle situation. So all I've done here is get that sine by itself, because I know that the sine of any angle of a right triangle is the opposite divided by the hypotenuse. So I want to draw the right triangle that's based off that statement. And of course I want to figure out what this adjacent is. I want to complete this right triangle. So I can just do Pythagorean theorem on that. That adjacent will equal the radical of my 3 squared minus my 5x squared. So if you do that Pythagorean theorem, you'll find that that adjacent is just the radical of 9 minus 25x squared. Okay, so let's just summarize real quick. We saw our problem. We found the entry of our trig sub table that would suit that Pythagorean theorem situation going on in that problem. And we were able to write out that substitution. And just remember, you want to draw the right triangle situation that this substitution describes. And the best way to do that is get that trig part of it by itself. Like I got sine of theta by itself, and that helped me create that right triangle. This right triangle is going to be necessary later. But now, what the name of the game is, let's just get all the x's out and put thetas in. This is trigonometric substitution after all. So we want, it's not u substitution where we got x out and put u's in. We're trying to get x out and put thetas in now. So here I put our x in for this x and this x. But I also got to get this dx out too, which just means I have to take the derivative of this. So here's the derivative right here of my x substitution. Of course I want to get dx by itself, so I multiply by d theta on both sides. And now I can replace this dx by all of this. So now that we've gotten all of our x's out and our dx out, and all of our thetas are in, including that d theta, now it's just a bunch of algebra that we have to roll with. So first I'm going to get these constants out of here. So this is going to be a 3/5 squared, and times another 3/5, well that's going to be a 3/5 cubed, and I'm just going to bring that outside the integral. That is a constant. So in the numerator, I just have a sine squared of theta times a cosine. So that's pretty simplified. Now in my denominator, I'm going to do this squared. So I have 3 over 5 squared times sine squared. So 3 over 5 squared is actually 9 over 25 times the sine squared of theta. And notice how if you take this whole thing and multiply it by that 25, the 25s will cancel. And now you can notice that we can factor out this 9 here. So now I notice that this looks like one of those identities that I learned about in the trig integrals section. So I know that 1 minus sine squared of theta, that's just equal to cosine squared of theta. And now algebra properties allow me to take the radical of each one separately. Just remember your algebra rules. This whole guy turns into a 3. And of course I can bring that 3 outside. The integral expression, because it's in the denominator, will have a divide by 3 out here. And if I do the radical of that cosine squared of theta, I'll just end up with a cosine. So that denominator cleans itself out pretty nicely. And of course, this cosine and this cosine cancel. So basically, after you use the table, after you formulate your substitution, after you remember to draw that right triangle, you just gotta basically get all the thetas out and x's in. And from there, it's just a bunch of algebra. You're just following the algebra. So this is the integral that we're left with. So now I'm thinking about how to take down this integral. So I'm exploring my options. I don't think a u sub is going to be good, because if we say u is sine, that means we have to see the derivative of that u, cosine, somewhere else in our equation, and we don't. So u sub's not looking good. I won't show it here, but integration by parts doesn't seem particularly nice either. But if you think about our trig integral section and all those identities that we have to know, we can use the half angle identity for sine squared. So I can write that in there. So of course this 1/2 here is just a constant. It can come out. That'll turn this whole thing into being divided by 6 instead of 3. And now what I'm left with is a much easier integral. Now the antiderivative of this 1 is just going to be a theta, and the antiderivative of this, I won't show the work, but that's just a u sub. We can get this to be a sine of 2 theta over 2. So we have taken the antiderivative. Of course, now we just gotta get x's back in here. And if theta is by itself, I can just use this guy, and I'll say theta is equal to the inverse sine of 5 times x over 3. Pretty simple. Now a lot of times you'll end up with something here that you can't use your original substitution on. I mean, we have sine of theta here, not sine of 2 theta. But again, your identities come to the rescue here. If you remember the double angle formula, sine of 2 theta is just equal to 2 sine of theta times cosine of theta. And of course these 2's will cancel. Now to get our sine out of there and x's back in, I mean, that's really easy. Just use that modified form of our original table substitution. But how about the cosine? We can't use this to get cosine. So this is where this triangle comes into play. Now remember, cosine of any angle is just the adjacent of that angle divided by the hypotenuse of it. So instead of writing cosine of theta, I can write the adjacent, radical 9 minus 25x squared, over the hypotenuse, which is 3. So here's our final answer here. So So this right here is one of the harder problems for trig substitution. So hopefully you were able to follow it. Remember, you use trig substitution whenever you see a problem that has something that looks like Pythagorean theorem, sum or difference of squares here. And depending on what sort of Pythagorean theorem equation you see, you'll use a different entry from this table. And you'll craft that substitution. And when you craft that substitution, remember to draw the right triangle that statement describes by getting the trigonometric equation by itself. From there, it feels very similar to U sub, you know? We want to get all the x's out and thetas in. So we got to substitute x in. And of course, we got to take that derivative to get the dx out. And after that, it's just a whole bunch of algebra until the end. And this triangle here is very useful in getting your thetas back in, as we saw here. So that's it for this video. If you want some more practice using trigonometric substitution, check out the practice video.